Okay, today let's talk about system design on Uber. So let me quickly write it down, the requirements over here. Design Uber. Make it bigger. Here. Okay, so let's discuss about the functional requirement. Okay, first of all, we allow Uber user to be able to request a ride and get the estimation from the Uber app. Get estimation about the time it takes and the price. Second of all, so we will need to make the request and matching the corresponding nearby riders. Matching, send the request, matching nearby driver. Third thing would be a driver can accept or deny a ride. So we will be able to allow either the rider and the driver to see each other's location and the location of themselves as well. See each other's location. So, and then we were gonna complete the ride. And probably provide reviews to each other. And payments, etc. But we can see how much time we'll spend, and this could be a to-do list of from the like functional requirements. So we basically do this. And then for non-functional requirements, so we can think of that. So we need strong consistency when requesting a ride and accepting a ride or denying. So we need the overall system to be highly available. High availability. Entire system. Also, we want a low latency when matching riders with drivers. And we would like to see a near real-time location check. Okay, these are the potential non-functional requirements, and we're like discuss when we're doing deep dives. Probably there will be some other non-functional requirements. For example, like compliance, GDPR, or related stuff. So we will mark them as to do. So other things we want to talk about would be, for example, APIs and entities. So for when we're requesting a ride, we might need to have a post request via HTTP to get a ride. And when like us, so this is the first one. And when we are matching, when a driver is basically accepting or denying a ride, we're gonna send another post. Like actually, it could be either a post or a patch, depends on how we're designing it. So let's go over to the diagram and the workflow, and then we could basically talk about APIs and data accordingly. So let me scroll down over here. So first of all, we will have a client, which is a rider on their mobile side. It's gonna basically request a ride from its phone of Uber app. So basically, we could use a API gateway, and we could basically, for example, using a AWS managed API gateway that has a load balancing functionalities and authorization authentication of probably potentially rate limiting functionalities over here. So I'm basically gathering these functionalities all together. Okay, so via this API gateway, we will have a ride request service. So what this service do is basically take rider's request. Second thing it does would be give estimation of the time and the price. So when we're giving estimation, we could either call third-party APIs or enabling some other services that we could basically call via API, and might be some algorithm calculation of it. but it's not part of the main functionality over here. So let's just keep it as like something like this to keep it simple. So whenever this ride request service is taking the rider's request, the first thing it's doing is going to write to a ride database. This it will write to the database first. What does this database mean? It could keep a ride DB, ride table. It could contain a ride ID, a time, status, user ID, and like a geolocation. Let's say basically we're having a location, for example, location da da da. And potentially, right, the status could basically could be requested or either requested or canceled or accepted or so. So it could be enum, like requested, canceled, accepted, denied. And as well as some other metadata, we won't be listing everything over here. So we could basically continue on this. So for the very first requirements, like it's basically giving the estimate to the rider over here. So we can basically get ride functionality. Okay, so once this rider basically request that ride, it's the rider request a service is basically sending a message to a separate service called matching service. On the matching service, it's taking nearby drivers status and then matching incoming ride request. Third one is send a notification to the rider, the driver, the matching driver, basically. Okay, so it's fairly clear that we're gonna need another client. We can call it a driver, probably driver one. So it's also going through the API gateway, and we will have another service that we could basically call it location service. So for the location service, we're gonna having some location DB that is basically quickly listen to the driver's location. So over here, it's it's fairly obvious that we could basically use WebSocket. So the flow would like this. So the driver go to the load balancer and help the driver to match a corresponding location service, and then the driver and location service could establish a WebSocket. WebSocket. WebSocket allows drivers and the location service to have bi-directional communication with each other. So without sending headers like HTTP request. So it will guarantee that it's very fast and low latency whenever the driver is reporting its location. And because of this, the location service is stateful. It's a stateful service that hosting a particular set of drivers information. So because of this, we could utilize the consistent hashing over here to make sure that the location service is matching. It's talking to a set of drivers that it hosts. So we basically could right here. So consistent hashing for so first thing to notice is a stateful service. We use consistent hashing. And it could be partitioned via geohash index. And also also we could basically use a driver's like a client ID as a plus for the partition key. So and whenever it listens to the driver's location, it will record to the corresponding database for persistent for durability of that location information. The reason we are gonna record everything of the location for the drivers is because our matching service need those data. So this database will be sending out to the matching service. So in order to make this quick, so I would recommend we don't use like a normal database, SQL, MySQL, etc. So we could directly use Redis. So the reason because Redis is supporting geohash index, first of all, and second of all, is most importantly, it's hashing, and it's much faster compared with we're querying database. So it's improving the throughput whenever we're reporting because the driver's this location is constantly changing. So we could easily apply some quick insertion and quick updating the values. over here. So we could basically partition the same way for Redis as well as the location service itself. First of all, they have to be on the same geohash. And the second one is that it's basically containing a same set of client ID. So basically the location service and the Redis could be having the same logic whenever we're using consistent hashing. So another way of we would like to use a consistent hashing would be the consistent hashing will allow us to scale very smoothly, because we could basically because for example, whenever we're using we're having like a concert at 10 p.m. and everyone over this district or this area is requesting the Uber ride to take them home. So in this case, this area and at this moment could be very hot, and consistent hashing allows us to enable new databases, a new Redis cluster and a new service cluster to scaling smoothly for the hotspot issues to be resolved. This is the first thing. And also for geohash, the reason we're gonna using geohash index is because we want to partition our entire ecosystem to via geohash. For example, we could have multiple data centers that is hosting the entire system like this in different areas across, for example, across US or across the world. So geohash index is another thing that we want to make sure we are handling edge cases. Actually for location-based service, we have two options. One is a quad tree, another is a geohash. So over here, the geohash compared with the quad tree, it's like having some advantages over here because the location for the riders and the drivers are constantly changing. So it's basically a constant changing scenario. It's not like a restaurant sitting on the same location all the way. So geohash is more flexible, is having more flexibility compared with the quad tree whenever we're updating the index. So this is the first thing. And geohash has some drawbacks over here because geohash is a kind of like it basically split the world into 4 parts, and each one have a number. It's overall as like the number we're using, it's increasing, it's more accurate. So the longer it basically have the more accuracy. However, the drawbacks. Talk back to the drawbacks of the geohash. The drawbacks of geohash is also obvious because it's basically so during the border of the geohash area that a rider or a driver belongs to, it's actually need to request the data from a different geohash location. So however, this could be resolved because, okay, first of all, geohash index is on disk is like a listing in order. For example, if a geohash is like AABB and the next one could be ABAA, so they're basically nearby. So it's easier for our servers to target to a corresponding other servers to get the information from that server. So for example, when we are basically having a location service or a matching service, and we want to request a corresponding, a different geolocation, and that belongs to a different partition. So we can easily get the hash value from our consistent hashing ring to target to that service to request that particular data from that service to ingest to our own service. So those are like those can be resolved by using geohash index and the partitioning via consistent hashing mechanism. So yeah, that's why we're choosing geohash over quadtree, and we're resolving the drawbacks from the geohash side. Okay, so let's like walk through whatever is left over here. So okay, we already talked about how the writer is basically requesting a write and provided estimation. And we basically send a request to our drivers. So it's better that we will have another, let's say, notification service. So when we are matching for a notification service, we could basically send it out to the drivers. Or if we don't use a notification service itself, we could basically utilize the the location-based service itself. But in order to make it more microservices, all these things, and the scaling individually, we could simply have a separate notification service to do that work. So the driver is basically accepting a ride or denying a ride. So like the matching service is also gonna so it basically could update the database itself of the status of this ride. Okay, so other things I would like to mention about the non-functional requirements. So we could basically replicate each of our service and database via geolocation. And the geohash index will be like the nearby geohash index should be relatively nearby on disk or nearby on partition when we're recording it to data, not only the services, but also the databases. So we basically need replicas for each individual service and for backups to maintain the high availability functionality. So so we already talked about how to make our matching low latency. So the first thing is that we make our location database as Redis as a cache instead of a database. And this is the first thing. And the second thing, as we mentioned, the matching service should be partitioned by itself via a geohash and a consistent hashing mechanism for quickly allocate to a particular geohash and like a particular set of drivers via a geohash, a nearby geohash location. So as well as whenever it needs some data to a different geohash box, it keeps the record from all the other servers that containing the corresponding data from that geohash index location. Yeah, so if we want, okay, the fourth one is near real-time location track. So we are basically establishing a WebSocket via the client, not only the riders, but also the drivers to our location-based service to report the location via WebSocket. So this could be near real time, and we don't need to send out the headers every time to keep that reporting instantly. So yeah, this is a real-time location track of our design. Okay, that's all I have as of now. So we definitely have any other things like for example the database. It's should get it. We could basically use a MySQL database, and we utilize the B tree structure for us to insert or request a particular data we want in the database, and we could basically use a single leader replication, and basically we partition it via the ride ID to our database. But overall, it also depends on so it's also need to be located within the same geolocation as the services, but have a replication to a different data center. So for higher availability, durability, etc. Okay, so I mean, another thing would be potentially useful is that we could basically use a message queue. For example, we can Kafka. We could basically use a Kafka over here to send requests to the matching service in order to keep our in order to keep the order. We could basically send to a Kafka instead of the in-memory message queue. So to keep the request in order and decouple the ride service and the matching service via a queue. So Kafka is a little bit better here compared with the other in-memory queue like SQS, because Kafka, we could basically partition the matching service all together with the Kafka as a consumer. And the Kafka allows us to make it more fair. For example, the rider 1 requested a ride before the rider 2. So Kafka makes sure that we are keeping that order in the same geolocation area. So that's why Kafka could be my number 1 choice over here. And yeah, and also as well, it's decoupling both of the service to make it more independent. So yeah, that's it. I think we are over time, and thanks for listening. I'm stopping recording the session.